In this chapter, we will focus on methods of proof, and we'll introduce different methods using the elementary number theory, because when we started our math education, we began with those numbers like integers and then fractions and then real numbers. So we are kind of familiar with some of the basic rules in the number theory field. So that's why we want to introduce the methods of proof using this field. Well, again, the 4.1 is just introduction. Here we'll talk about different methods, including direct method and indirect method. And we'll talk about how to write proofs in standard style and prove different types of statements and disprove existential statements. And most important technique is to generalize a conclusion from the generic particular. So we'll talk about all those. First of all, we have to make some assumptions. Please review the Appendix A. Those are the basic algebra laws that you should be familiar with. So I would say quickly skim through all the laws listed in the Appendix A. Second, we are going to assume that for all objects A, B, C, A is the same as A, okay? If A equals B, then we can conclude that B equals A. And if A equals B and B equals C, then we conclude that A equals C. So those are the fundamental rules that we have to agree upon. We don't prove those, we assume they're true. For all objects A and B, if A equals B, then we may substitute B whenever we have A. So substitution is allowed. That's quite intuitive. And the next one is there's no integer between 0 and 1. The set of integers is closed under addition, subtraction, and multiplication. What does that mean? I think this first part is pretty straightforward. We assume no other integers between 0 and 1. Now when we say the set of integers is closed under addition, that means if you pick any two integers, that means, so under addition, that means pick any arbitrary integer, one integer plus another integer. When we say close, that means the result is still a new integer. Will be another different integer, may or may not be the same. So that means close. That means integer add integer, the result is still integer. Therefore, similarly, integer is closed under subtraction. That means integer minus integer is still integer. Simply change this to minus sign. That means this is closed under subtraction. And when we say close under multiplication, that means integer times integer, the result is an integer. The closure, this property is not true for division because obviously 1 divided by 2, which is 1/2, this is 0.5. This is no longer integer, right? So therefore the division, the integer is not closed under division. And another agreement, let's make a agreement here without, unless specifically stated. Otherwise, all the lowercase letters in this section, actually in most sections in this chapter, will by default, it represents a integer. It represents integers. Okay. All right. So those are the agreement that we want to make. And now let's talk about the first, introduce the first definition. Okay. By the way, definitions are the building blocks of all the other results. So we always begin with definition, and then using definition we derive some results. Sometimes we call it theorem if that result is big enough. And then we also from the definition plus the theorem we can derive some other theorems or other propositions or other lemma or corollaries, things like that. Okay. Now, so let's begin with the first definition. An integer n is even. So we are defining what is even, okay? If and only if you remember, that means if and only if n equals twice some integer. So my first task for you is think about how would you write this into symbolic form. Okay, so now so pause a little and then try to think about how you would write this into symbolic form before you resume the video. Now an integer n is even, so basically this is just saying n is even. If and only if, okay, n equals, that means n equals, right? N equals twice some integer, okay, this is a keyword, some, that means for some integer, n is equal to twice of that integer, right? So therefore, if and only if you must be able to find an integer, there exists an integer, let's call this k. Again, we assume that lowercase represents integer, but at the moment, so I'm gonna say k from integer, right? And then the exist usually follows the such that n is twice of this integer. Let's go back and reread and compare this symbolic form so that you make sure that you agree with that this is actually the symbolic form of this definition. So we say n is even if and only if n equals twice some integer. N equals twice some. Some means there exists some, right? So therefore there exists k. And what is k? K is integer, so k is integer, therefore I use this symbol. So n is even if and only if there exists k in integer such that n equals twice of this integer to k. Now let's take a look at the next definition. An integer n is odd if and only if n equals twice some integer plus 1. I hope that you can quickly write this down. The symbolic form, n is odd if and only if there exists k in z such that n is equal to twice some integer, so twice of this k plus 1. Now after we translate this into the symbolic form, the next question I would like to ask is, what action do you have to do to prove a given integer is even or odd? So like, how do you prove if a given integer is an odd or even? Then you look at this definition, right? You're going to read through that. It says there exists k. That's the training that we received from last unit. How do we correctly interpret like quantified statements? So when we see there exists, that means your job is to look for this guy. So you look for a k so that n is equal to that result. So therefore, your job, because the exist symbol, that means your job is to find or you look for such k, right? Such k. So you are trying to find the k. Once you find the k so that it's true here, then you say it's even if it is true here, and then you claim it is odd. Now let's try to apply the definition to justify each of the following. Is 0 even? Now if it is even, suppose if you, before you conclude it is even, if you are able to find a k which is an integer, so that this 0 is equal to twice that k, then you can conclude it is even. So therefore I'm going to give a try, okay? So in other words, your job is to look for a k which is an integer. Again, in the future I may skip this, writing this out. such that you're questioning 0, so such that 0 is equal to twice of the k. So your job is to try to look for, are you able to find an integer so that 0 is equal to 2 times 0? Of course, yes, we can. Yes, right? Because we are able to find a k, because 0 equals 2 times, that's the k that, 0. K is 0. So we are able to find a k, which is 0, so that 0, which is the one that we are trying to justify, equals 2 times the integer, which is 0 that we just found. So because of this reason, we claim that 0 is an even integer. So we are using this definition. Now let's take a look at the part B. Is negative 111 odd? So in other words, if you are able to find such a k so that negative 111 equals 2k plus 1, then you can claim it is odd. So therefore, I'm going to give a try. Okay. So in other words, are we able to find such a k? So 2 times, this is the k that we are looking for. 2 times k plus 1, that's the definition for odd integer. So are we able to find such k so that this is true? Now obviously a little algebra reveals that if this is negative 56, right? Let's check. 2 times negative 56, which is negative 112. And then if you plus 1, which gives you 111. So therefore, we are able to find such k, which is integer, so that negative 111 is equal to twice of the k plus 1. So therefore, this is, yes, it is odd. So therefore, I'm going to make a conclusion, yes, because there exists, right? There exists k equals negative 56 so that this n, which is negative 111, equals 2 times this k plus 1. So therefore we conclude it is yes. Alright, now let's continue. Is this guy even 6 times ab cubed? Is it even? Then we're gonna again try to, remember the agreement. All the lowercase, if we don't, unless stated, otherwise they represent integer. So a and b are integers here. So is this even? Then you're gonna say, can you find a integer so that this guy is equal to 2 times, this is the integer you're gonna find, right? Okay. Obviously, by looking at this guy, this is actually 2 times 3ab cubed. Okay, 2 times 3ab cubed. And because a is integer, b is integer, so we already assume the product of integers is closed. Therefore, we do know that the products should be integer. In other words, this guy has to be integer because a and b are integer. Therefore, product will be integer. So I'll say yes, because there exists k, where what is my k? K is this guy, 3 times ab cubed, and this guy is an integer, such that the number that this term we are talking about is equal to twice of some integer, right? So therefore, according to the definition, this is even. Let's take a look at this one. It's getting a little more and more involved. Is this a even? Is this term even? Is this guy turns out to be even? Now, in other words, you are trying to look for, are you able to find something so that this is equal to twice of the integer? So are you able to find something so that this is twice some integer? The answer is yes. You just simply factor out the two. So you have AB plus 5RS minus 8. So do you see that this is an integer? This is an integer. And this is your k. Basically, you let this be your k. Then this term is equal to 2 times k. How do I know this is integer? Because a and b are integer. Therefore, the product is integer. R and S integer, so 5RS, the product of these three is an integer. And the sum of these two integers and sum and difference of integers are integer. So therefore, I know that this has to be an integer. And therefore, when I write this into twice some integer, this automatically proves this whole thing is even. So I will say yes. Because we can find k, right? There exists k equals ab plus 5rs minus 8 such that this whole thing is equal to 2 times the k. I'm going to move this here so that I'm going to write it out nicely, such that 2ab plus 10rs minus 16k is equal to that, and which is 2 times k. So which is 2 times k. Now let's move on. Is this odd? Again, how do we prove that it is odd? Certain term is odd. If you are able to find a k integer such that this term is equal to twice that integer plus 1, then you can conclude that it is odd. So therefore, let's give it a try. So I feel like yes, this is going to be odd because this guy is equal to 8mn plus 2 plus 1, right? And the reason I isolate 1 because I'm trying to make this happen, like 2k plus 1. I need to look for a k. That's the action that I have to take. And then this is equal to 2 times 4mn plus 1 plus 1. Do you see the k? I hope that you're able to call this as k. This is an integer. This is the integer. Because m and n integer, so product is integer, addition, adding integer will be integer. So therefore, this is in the form 2k plus 1, right? So but I'm going to write it out nice. So I'm going to say yes, because there exists k equals 4mn plus 1 such that this guy equals 2k plus 1. So whenever you are successfully find a k so that this term equals 2k plus 1, you can conclude this is an odd. This is odd for sure, no matter what mn is. Now the last one. Okay, so the last one, you can sometimes it takes a little trial and error. And in this particular case, if you try, say suppose b is 1, a is 1, okay, then you can see this whole thing becomes 4 minus 3 plus 17, which is equal to 18, which is even, right? Now if you try b is 1, a is 0, then you can see that this becomes 4 times 1 plus minus 0 plus 17, which is 4 plus 17, which is 21. It becomes odd. So it really depends on what a and b are, and I really cannot write this into a definite like a 2k form or 2k plus 1 form. and it depends on what A and B. Sometimes it's even, sometimes odd. So therefore, this can be odd or even, depending on A, B. So we cannot simply conclude it is odd, it is it is even. Just it varies. So that's the first part of this section. We introduced two concepts, even and odd, and we kind of proved, not officially, we are not writing a very rigorous proof yet, but we are trying to apply the definitions so that we justify whether each one of those is odd or even. In the next video, we are going to talk about prime numbers.